Take a look at Alan Baker's animation here. The Matchstick Man tries to cross a valley but fails because the kinetic energy he possesses isn't enough to overcome the valley's potential energy. That's why he needs to increase his energy by starting farther back. Eventually, he makes it because his kinetic energy surpasses the potential energy of the valley. This principle is essential. In physics, everything revolves around energy. You can't overcome a barrier if you don't have enough energy because, at its core, the barrier is energy itself. For example, why can't you fly? It's because there's an energy barrier, the gravitational field. When you jump, your kinetic energy isn't sufficient to overcome the gravitational energy, which grows stronger the higher you go. But if your energy were sufficient, you could soar into the sky. The same applies to walls. Walls also have energy depending on their thickness and material. If your energy isn't enough, you won't be able to pass through them. However, if your energy exceeds the barrier, you can break through. Interestingly, this law of physics can be violated in the quantum realm, specifically within atoms. A particle can pass through a barrier even if its energy is insufficient. This phenomenon is called quantum tunneling. Now, can quantum tunneling be applied to the human body, allowing us to pass through walls like vision? That's what we'll discuss in this video, but to understand it, you need to learn about atoms and the quantum world. Be prepared to be astonished, because discussing atoms and quantum physics can leave you scratching your head. That's why before we begin, get your minds ready and prepare your faith, because we're about to dive into a discussion that could blow your minds. Everything in this world, including your own body, is made up of atoms. Atoms are incredibly small, millions of times smaller than grains of sand. They're so small that it's estimated our bodies are made up of this many atoms. However, atoms aren't the smallest particles. Atoms themselves consist of even smaller particles, electrons, protons, and neutrons. Here's the funny part, the depiction of atoms you often see isn't to scale. If it were, electrons, protons, and neutrons would be invisible because these particles are millions of times smaller than the atom itself. Imagine if an atom were enlarged to the size of a soccer field. Its particles would be as tiny as grains of sand. This means most of an atom is empty space. So here's the big question. If atoms are mostly empty space, doesn't that mean our bodies are empty too? If our bodies are empty, why don't we pass through one another like ghosts? Why do our bodies feel solid? Here's where it gets interesting. Remember, atoms are surrounded by negatively charged particles called electrons. Any charged entity, whether positive or negative, creates an electric field. This field stores energy, causing particles with the same charge to repel each other. This is known as the electrostatic force or Coulomb force. This electrostatic force prevents atoms surrounded by electrons from ever touching. They repel one another, much like the same poles of magnets. So here's the surprising fact, even though you feel like you're touching something at the atomic level, you're not actually touching it. The sensation of solidity is just the manifestation of the repulsion between atoms. It may sound nonsensical, but that's the reality of studying atoms, and we haven't even delved into quantum physics yet. Once we do, it gets even more complex, as there's another reason why our bodies feel solid. In quantum physics, specific laws govern particle behavior, such as the Pauli exclusion principle. This principle states that no two electrons can occupy the same position and state within an atom. For example, if one electron in an orbit spins clockwise, the other must spin counterclockwise. This rule establishes electron configurations, determining how electrons are arranged within atoms. It's not random. This is why scientists could organize atoms into a periodic table. based on their electron configurations. However, the Pauli exclusion principle has another consequence. Atoms cannot overlap with one another. Why did it happen? Because electrons already occupy specific slots within the atom and cannot randomly jump into another atom's orbit without permission. Instead, atoms collaborate to fill each other's electron deficiencies, but this only happens in their outermost shells. This is what allows atoms to bond, forming molecules and enabling chemical reactions. In short, both electrostatic forces and the Pauli exclusion principle act as barriers preventing atoms from overlapping. Combined with atomic and molecular bonds, these factors make our bodies feel solid and prevent us from passing through walls. But the story of atoms doesn't end there. In quantum physics, an object cannot be treated as a physical entity in the way we see it daily. For example, you can't think of an electron as a small spinning ball. Instead, it must also be viewed as a wave. This wave is a probability wave, meaning electrons don't have definitive positions, they can be anywhere. The only thing scientists can do is calculate probabilities, the likelihood of an electron being in one place versus another. This is described using a wave function. This peculiar behavior allows electrons and other particles to interact with barriers in a unique way. Earlier, we mentioned that in classical physics, an object can't pass through a barrier if its energy is insufficient. However, in quantum physics, because electrons have many possible positions according to their wave functions, there's a chance they'll appear on the other side of the barrier as if they've tunneled through it. This phenomenon is called quantum tunneling. If you could control all the particles in your body to perform quantum tunneling, you could theoretically pass through walls like vision. But this is nearly impossible. Why? In the quantum realm, everything is about probabilities. The likelihood of quantum tunneling occurring is extremely small. The wave function diminishes as it crosses a barrier, so quantum tunneling only happens in very specific scenarios. Even if millions of particles attempt to tunnel, only a few might succeed. For a human made up of countless particles, the probability becomes astronomically small. One physicist calculated the odds of the flash phasing through a wall using quantum tunneling, and the results were staggeringly low. Yet, without quantum tunneling, life as we know it wouldn't exist. For instance, quantum tunneling is happening right now in the sun. The sun shines because of a nuclear reaction called fusion. Fusion occurs when dihydrogen nuclei combine to form helium, releasing energy as heat and light. The problem is, for fusion to happen, dihydrogen nuclei must get extremely close, but electrostatic forces prevent this. This is where quantum tunneling comes into play. Dihydrogen nuclei can pass through the electrostatic barrier via quantum tunneling. Although the probability is small, the sun contains an immense amount of hydrogen, trillions of tons. With such vast numbers, millions of tons of hydrogen undergo quantum tunneling, enabling fusion. It's estimated that 600 million tons of hydrogen are converted into helium every second. Without quantum tunneling, the sun wouldn't shine. Quantum tunneling also occurs in photosynthesis. Sunlight particles, or photons, penetrate chlorophyll in leaves via quantum tunneling. Without it, leaves couldn't photosynthesize, which means no oxygen or food for humans. So this isn't just about the flash or vision passing through walls, it's about life itself. Without quantum oddities like tunneling, we wouldn't exist. These laws, which allow some atoms to pass through while others cannot, are intricately designed to sustain life as we know it.